Hello again. Right, now let's look at topic 3 in your module, that is the design considerations of geostructures. So we'll be looking at 3, there will be the foundations, the retaining structures, and the earth dams. So let's start with the foundations. And when we talk about the foundations, we always start with the shallow foundations, which I believe you already learned some of these in the construction technology course. Okay, so the loads that are acting on a foundation are typically the vertical ones, and the uplift, and also horizontal loads and moments. Alright, as you can see in this diagram, vertical compressive load, uplift forces, horizontal loads, and also moments. Okay, and for shallow foundations, the way we define it is that we say that the breadth of it B is about the same order of magnitude, about the same size as your depth. If this D, as you can see, DF is effective depth. That's from the surface of the ground right up to the base of your foundation, right? And we say here that B usually is larger or the same as D. Okay, and in fact, some books will say that is the ratio of D over B is no more than 1. Largest is 1. They say same size as D and B are the same size. Some books will say that it should be about 2.5, but generally it's no more than 3. That is what we can see from the textbooks and the standards. Alright, and the mechanisms that the soil resists the stresses coming up through your foundation are actually these as per the forces we discussed earlier. So you can see here, to take the vertical forces, we have the bearing capacity. Similarly, for your dead weight is bearing capacity to take it, and for any horizontal forces coming in, it will be a sliding friction at the base of the foundation. And for moment, due to eccentric loads, remember we learned that in chapter 2, then we could have a situation where we have a redistribution of a bearing pressure, alright, to make it stabilize again. And here, quickly, the types of shallow foundations that we commonly come across. The first one are the strip footings. So strip footings, you can see, and the top part of these diagrams, these are the side view, as you can see, and whereas the bottom row are showing you the plan view. Okay, so these are the ones that you see from the top, these are from the side. So from the side, a strip footing will look like this. You can see they're actually staggered like steps. So the bigger ones, the base is bigger, and it goes up, it's slightly smaller until it connects with the wall or the column coming down. Usually for strip footing, we have a wall sitting right through it. Right? You can see above it. So from the top, you can see them looking like these strips. For the individual ones, individual pads, we call them footings or pad footings. This is how they look like. You have a column coming down and individual pad that's taking the load. If you combine more than one, sorry, of course there's more than one, there's 2 or 3, you call them a combined footing. Can you see here? Right? There's a slab or a tie beam that will tie 2 pads together, tie 2 footings together. Alright? And if you have too many of these footings coming around, so many of them, you might as well just combine them and make it into a rough, which is essentially like a slab. We'll see more about this rough footing later on because they can be very useful in certain situations. Alright? Now, what about deep foundations? Similarly, we are talking about a foundation taking the load from the top right to the bottom, taken by the soil. And in this case, your effective depth over the breadth ratio should be more than 1, obviously, because for the shallow ones, they shouldn't be more than 1. Okay. What about the loads that are acting on your deep foundation? Same thing. You have the loads coming down from the top. Those are the vertical loads, and they could be taken by who? By either the ends, they are the tips of the piles, you call it end bearing, or the friction on the side of your piles. Those are called the skin friction. They're giving the frictional resistance against the load pushing the foundation down. And you also have the dead weight of the foundation itself, of course, because at the top you have your pile caps, and you could have lateral pressure coming in and also the moments. So you can see there are the similar loads coming in as for your shallow foundations. Now, this is one that is interesting and important. We are talking about the uplift forces, horizontal loads, and so moments. They are especially dangerous and risky when you're looking at structures that are tall and slender, high-rise buildings, alright, typically towers, alright. And these why? Because the forces coming in like winds, earthquakes, any other reasons, machineries, sudden exposure will cause lateral loads, and these loads are going to cause what? Uplift. Let's look at one example here. Alright. Okay. This is a typical situation for a transmission line tower. We have seen this along the highways, plenty of these. We call them pylons sometimes. big towers, they're just steel structures, right, frames, and you have cables, heavy cables connecting to the next tower and so on. So these are very tall and slender structures, as mentioned earlier, and they are subjected to horizontal loads like wind, sagging cables, the load of the cables themselves, any vibration coming in, earthquakes and things like that. And what you see here is that if you do not have a foundation that is strong enough, it would actually cause the tower to be pulling up the foundation itself. Can you see? Yeah. So in this case, normally the foundation is such that, yes, it's a deep foundation, the power going down, and they have an enlarged base. Look here. Alright, and these are usually bored piles, so they bore a bigger hole at the bottom, and as they come up, the shaft coming up, it will pump in concrete at the base, so a bigger shaft. So you can see it's like causing a big bulk down there. So when the force try to pull it up, these uplift forces, it's difficult to pull it out. It's not it can't be pulled up, it can be pulled up with the forces beyond the resistance, but this is what we do to enhance the resistance against horizontal loads. Right. And another situation where horizontal forces can be detrimental to your piled foundation, as you can see here. There are 3 layers of soil, imagine, okay? The non-liquefied, the loose liquefied, and the non-liquefied again. Basically, this is a situation where there's an earthquake, groundwater rising quickly, and this layer where they have loose sand, the water will start to push the sand particles apart, and you can imagine when the soil sand particles are literally floating around in the water matrix. So this layer is no good for any load bearing, and these horizontal loads coming up from the top because of earthquake. So this part, the middle part of the soil layer, will be giving no help. Alright, giving no help to the resistance provided by the piles. Hence, the pile in the middle region could be breaking or could be bending. Alright. Similarly, in this, the next slide we see the moment effect. So when horizontal loads come in, they will cause eccentricity to the actual loads that are being transferred to the piles. And same here, if you have a strong layer, sand leaching, strong layers, top, bottom, sand leaching, liquefiable layer, loose sand typically, you could have your piles breaking in the middle. Or if the piles are stiff enough to be held in the ground, you could have the superstructure that's a building over the top to be toppling over. Okay, the effect of moment. And in situations where we know the piles could be subjected to horizontal forces like these, in Malaysia we don't have much earthquake. We only have the after effects or the far away waves coming in from Sumatra, Philippines, and so on. So these structures, the foundations for these structures need to be tested in terms of horizontal loads. So it's the same like doing a pile load test from the top, maintain load test. Now the loads are being applied from the side. As you can see here, dead men are simply the dead weights. You have a jack coming horizontally to push against the pile to measure, see what kind of reaction or what kind of loads that the pile can be taking as per your design. Alright. That's how it works. And here, quickly, the types of deep foundations that we have commonly used, single piles like this. It could be a drilled pile. Remember I talked about, if you have drilled piles, then you can have a bigger base like this, right? Above or under rim bases. And you could have a caisson or a pipe pile like this, meaning that the inside of it is hollow. And when you imagine pushing these big pipe down, eventually you could have soil coming in, a plugging effect here. Alright. Moving on to the right, you have some tapered piles. These are more like the timber piles, which are not very common these days anymore because of sustainability issues. And again, we could have a pile that is composite. You push in the pipe, then you put in the concrete if you want it to be super strong. Alright? Okay, and last bit of this deep foundation is that we'll be looking at pile groups. We rarely use single pile to sustain the load. We usually have a group of them. We'll see later on what is the purpose of that. As you can see in this illustration here, like in the side elevation, you can see you have thought that, wow, it's just 1, 2, 3, maybe 3 piles. Actually, if you look from the top, the plan view, you can see that actually a group of 9 piles, or it could be a group of 4 or 3, things like that. Okay. Similarly here, that is for a flyover. You have pile groups coming in to support the structure. So because flyovers are just like bridges, and because they are rising high, and it could be subjected to wind loads and all, so the piles have got to be very strong to sustain the load that's coming in. Not just the dead load, there are also the dynamic loads coming in from the traffic, from the wind and all. Alright, we'll pause here for a bit and move on to the next section.